Hello, nice to meet you. I am Motohiko Kusakabe in Beihang University in China. Because of some unexpected situation, I'm now lecturing instead of Professor Kajino, who was originally planned lecturer. Although this is an unexpected situation, I'm happy to have a chance to share some fundamental things, knowledge about the neutrino nucleosynthesis with you. So, this lecture is about supernova neutrino nucleosynthesis, laboratory for fundamental physics. I hope that after this lecture, you understand the meaning of this title. And this is the first part of the lecture. It contains neutrino properties and neutrino oscillations in vacuum, constant electron density, and stars. First, neutrino properties. So this picture shows standard model particles. So these are quarks and leptons, and gauge bosons and Higgs. All of them have been already detected in experiments. And as you know, excepting the very weak gravity, three forces operate to elementary particles. And today's target is neutrinos, neutral leptons listed here: electron, neutrino, muon neutrino, and tau neutrino. And those neutrinos are elementary particle with spin 1/2 in standard model physics. And they have three flavors. And only left-handed neutrinos and right-handed antineutrinos interacts. And exactly speaking, neutrinos has mass, so it interacts by gravitation also. Then, neutrino has only two interactions, weak and gravitational interactions. Gravitational interactions are usually not important in physical processes. But today's lecture on the neutrino process in supernovae, the gravitational interaction of neutrinos are not important. So in the standard model, interactions are described by gauge theory that involves interaction of fermions with spin 1/2 and the mediator boson spin 1. And the standard model physics is described by some groups that include gauge theories. SU2 cross U1 for electroweak interaction part and SU3 for strong interaction. And this is a basic vertex of the gauge theory. Boson is exchanged and fermion couples to this boson. And this table summarizes the 4 interactions in the universe. As you know, there are 4 types: electromagnetic, weak, strong, and gravitational interactions. Associated gauge bosons are listed here. And this is the symbols for these bosons. And electromagnetic interactions are relevant for almost all phenomena around us, including radiative nuclear reactions. And weak interactions are relevant to beta decay and neutrino scattering, and so on. Strong interactions are relevant to the interaction associated with quarks. And gravitational interaction operates between masses. And one of the fundamental interactions is weak interaction. It is relevant to beta decay and scattering, weak interaction scattering. It is described by vector and axial vector interaction type, and mediated by weak bosons, charged boson W plus minus and neutral Z0 boson. These gauge bosons has typical mass of 100 gigaelectron volt. And the interaction range is very short. It is inverse of the mass scale. Because of the heavy gauge boson, the interaction range is very short. And here is some property of the weak interaction. If the reaction occurs at low energy compared to the weak boson mass, then interaction is weak. That is because the scattering cross-section, for example, scales as the Fermi coupling constant squared. That is 1 over weak gauge boson mass to the fourth power. So because of heavy mass, the cross-section is hindered. But if the reaction occurs at high energy compared to the gauge boson mass, interaction is just strong as electromagnetic interaction. So as far as we consider the reactions at low energy, this weak interaction is very weak. And this weak interaction is only relevant for left-handed particles and right-handed antiparticles. What is left-handed and right-handed? If the momentum direction is the same as spin direction, that state is called right-handed, and the opposite case is called left-handed. This is one of weak interaction property. And the coupling constant of the weak interaction is Fermi constant to the 1/2 power. And the scale of the Fermi constant squared is this one. And as already introduced in the previous slide, weak interaction is a very short range force hindered by 1 over mw. So it doesn't work at long distance, just at the distance corresponding to 1 over mw. And this weak interaction is relevant, for example, for pion decay and muon decay. For example, positively charged pion is a state of up quark and anti-down quark. And it emits W plus, and W plus decays into mu plus and nu mu. This pion decay is mediated by this weak boson. Also, at the muon decay into 1 electron and 2 neutrinos, weak interaction is relevant. Next, let's see the types of neutrino reactions. There are 2 types of reactions, depending on the gauge bosons exchanged: charged W boson or neutral Z boson. First type is neutral current reaction. In this reaction, no flavor change occurs through the reaction. For example, up quark stays as an up quark, and electron stays as an electron. On the other hand, in charged current reaction, flavors change. For example, up quark is converted to down quark, and electron is converted to electron type neutrino. Let's see the diagram corresponding to the neutral current reaction first. These three diagrams are corresponding to the Z0 decay. And this is relevant to the process that electron exchanges Z boson and stays as an electron. Also, similar diagram exists for electron type neutrino and quarks, for example. By combining these interactions, these kinds of scattering process is possible. This reaction is scattering between two electrons, and this is scattering between an electron and an electron type neutrino. So the particles in the initial state is the same as those in final state. And the second type is charged current reaction. These three diagrams correspond to the W plus minus decay. So in this process, electron exchanges W boson and it is changing to the electron type neutrino. Also, this is changing from the electron type antineutrino into the positon. This case is the conversion from the down quark to up quark. Corresponding scattering process includes these diagrams. By combining these vertexes, this reaction is possible. This is scattering between electron type neutrino and electron. And exchanging W boson, it is converted to electron and electron type neutrino. So in this reaction, the particles in the initial state is the same as those in the final state. But in this case, up quark and electron is converted to down quark and electron type neutrino. So flavors are different between initial and final states. If you add lines for up quark and down quark to this diagram, it becomes this form. Up, up, down is proton. Down, up, down is neutron. So this diagram is corresponding to this reaction. The conversion from proton plus electron to neutron plus electron type neutrino. And this is the weak reaction for conversion of proton and neutron. So let's classify weak reactions of nuclei. It includes electron capture of proton and neutron beta decay and inverse reactions of them. For example, this is the weak interaction converting proton to neutron by W boson exchange. So, and by changing the diagram a little bit, this reaction is also possible. That is neutron decay into proton plus electron and anti-electron neutrino. For these two reactions, reverse reactions are also possible. Reverse reaction of this reaction is neutron electron neutrino scattering. And this is called inverse decay of neutron. That is three-body fusion reaction to produce one neutron. And here we list some types of reactions, weak reactions of nuclei. Bracket ZA means the nucleus with mass number A and charge number Z. If that captures electron and emit electron type neutrino, that reaction is called electron capture. Similarly, if some nuclei capture positron and induce weak reactions, then it is called positron capture. Also, some unstable nuclei can decay by emitting electron and anti-electron neutrino. That is called beta decay. And a corresponding reaction for positron emission is beta plus decay. In addition, neutrinos can induce weak interaction, as shown here. This is charged current neutrino reaction. This is charged current anti-neutrino reaction. So, these reactions are relevant to the neutrino nucleosynthesis in supernovae. One important property of neutrino, distinguished from other elementary particles, is the smallness of its mass. Neutrinos are extremely light. For example, some cosmological bound gives the sum of the mass of 3 neutrino species that is smaller than 0.152 electron volt. And from neutrino oscillation experiments, squared mass difference between mass eigenstates is constrained as shown here. It depends on so-called mass hierarchy of neutrino introduced later. But anyway, mass square difference is this small value. So compared to other elementary particles whose property is listed here, neutrinos are special in its smallness of mass. And let's review a little bit about the history relevant to neutrinos. Neutrinos only interact by weak interactions and gravity. So it has no electromagnetic and strong interaction. It means that experimentally, neutrinos are hard to detect. Neutrinos are postulated theoretically by Pauli to account for the energy conservation at beta decay. And neutrinos are taken into account in beta decay theory by Fermi. So neutron decays into proton and electron. But there should be another particle, electron antineutrino. And Hovan, Linus, Harrison, Cruz, and McGill found a neutrino through this reaction. If this reaction is induced, positron can be detected through 2 photons from pair annihilation. And generated neutron can also induce gamma ray emission. So detecting these photons, the existence of neutrinos are detected. And Homestake experiment detected electron type neutrino emitted from nuclear fusions in the sun. But experimentally, it was found that NUE flux, electron type neutrino flux, is smaller by a factor of 3 than theoretical estimate. And this discrepancy was called solar neutrino problem. And nowadays, we know that this solar neutrino problem was caused by neutrino oscillation. During the propagation of neutrinos, its flavor changes. And it is related to the mass squared difference. That is small, but it has been experimentally measured. So, cosmic rays, energetic particles coming from the outer out of the Earth. These cosmic rays produces neutrinos through formation of pions and its decay. And one mystery about the cosmic ray generated neutrinos is that without assuming neutrino oscillation, the neutrino detection experiment is not explained. For example, here is neutrino detector near the surface of the Earth. And if neutrino flavor changes through propagation, the event rate is different depending on the direction of the neutrino propagation. So some neutrinos come from the sky, some comes from the central region of the Earth, and some passes through the Earth in some direction. And this figure shows the number of events of neutrino detection as a function of the angle of neutrino direction. If we don't assume the neutrino oscillation, then event rate is predicted as shown by this red line. But the observation suggested these data points. This dependence on the angle of neutrino direction is explained by considering the neutrino flavor change. And it was a real solution to the solar neutrino problem. So let's briefly mention the importance of weak interactions in our universe. Weak interaction is weaker than electromagnetic and strong interactions. Because of that, in the early universe, the weak interaction becomes unimportant firstly. This figure shows thermal history of the universe. Starting from the hot and dense Big Bang, universe expands and cools down. In the initial state, the density and temperature is large enough. So not only electromagnetic and strong interactions, but also weak interaction is fully operative. Because of that, before the Big Bang nucleosynthesis, weak interactions are not so weak. It's weak, but the weak reaction rate is large enough. Because of that, even neutrino and anti-neutrinos are in thermal baths, interacting with other particles frequently. But before the Big Bang nucleosynthesis, this weak interaction decouples. I mean that weak interaction rate of neutrino becomes smaller than the cosmic expansion rate. So after this decoupling time, neutrinos has no chance of interaction with other particles, and it becomes neutrino background. And as you may know, the nuclear reactions freeze out after the Big Bang nucleosynthesis. And after that, electromagnetic interaction between photon and background electron freezes out long later than the Big Bang nucleosynthesis epoch. And yes, freeze out of electrons, interaction of electrons from background photon also occurs in late universe. So In this way, in the expanding universe, weaker interaction decouples earlier. So weak interaction is the first interaction that decouples. And in the first 3 minutes of the Big Bang, primordial nucleosynthesis is expected to occur, as proposed by alpha, beta, and gamma elements originating from a Big Bang. In this paper, it was considered that various nuclei observed today are formed from reactions of neutrons in the early epoch. But in fact, the situation was a little bit different. Big Bang nucleosynthesis starts from neutron and proton nuclear matter, not purely by neutron. And the ratio of neutron and proton is controlled by the weak interaction. So this weak interaction determines the neutron over proton ratio. In such a situation, only hydrogen and helium are produced significantly, and trace amounts of beryllium-7 and lithium-7 are also produced. And yes, this is a present understanding of the Big Bang nucleosynthesis. And in Big Bang nucleosynthesis, weak interaction is important because it determines the neutron to proton ratio. This ratio determines the final abundance of the BBN. So, as we saw here, in the expanding universe, weak interaction firstly decouples. So, the remnant of the hot Big Bang would remain as cosmic background neutrinos. These cosmic background neutrinos are very abundant. Let's give some estimate for the number density of background neutrinos. First, as you know, this universe is filled with cosmic microwave background. Its number density is given by this equation. This is based on the Planck distribution of the photon energy distribution. Theta 3 is theta function of 3. That is almost 1.20 something. T is cosmic temperature that has been measured. And we know that cosmic microwave background radiation has this energy number density, 400 per cubic centimeter. So it's very abundant. Similarly, background neutrinos has this large number density. So each cubic centimeter contains 300 neutrinos. But because of the weak interaction, it's hard to detect this cosmic background neutrinos. This is relation between the neutron number density and photon number density in the cosmic background. 3 is just the number of species, number of generation of neutrino. 4/11, this is related to the fact that the electron-positron annihilation occurs after the neutrino decoupling in the expanding universe. And 3/4, this is just a statistical factor. Photon is boson. Neutrinos are fermions, so there is some difference in statistics. Anyway, the number density of background neutrinos are of this same order of that of background photons. That is very abundant. So, the universe is the first site of neutrino production, and the second site of neutrino production is atmosphere of our Earth. Some example was already explained, associated with the solar neutrino problem. And the third site for neutrino production is the Sun and other stars. For example, this figure shows the helium synthesis inside a star. Two protons fuse and deuterium is produced. At this reaction, one neutrino and positron is emitted. And yes, deuterium and proton can fuse and it is converted to helium-3, and two helium-3 is converted to helium-4 and two protons. Through this formation of helium-4 nucleus, two neutrinos are produced here. So nuclear reactions inside the stars produces neutrinos as byproducts. This figure shows the flux of neutrinos calculated as a function of neutrino energy, originating from nucleosynthesis inside the star, inside the Sun. So weak reactions that operates during the nucleosynthesis produces these fluxes of neutrinos. And fourth site of neutrino production is core quarks supernovae. Here, a supernova is found. This region is measured by various wavelengths of photons observations. And yes, here is some structure of the supernovae. And neutrinos coming from the supernova has been already detected at the time of supernova 1987-8 that occurred in Large Magellanic Cloud that is very close to our galaxy. And this figure shows the signals of the neutrinos as a function of time. And there are several detections. But in this short period of time, there are some groups of neutrino detections. And it corresponds to the neutrinos coming from this supernova. And what is supernovas or supernovae? Yes, before the supernovae, there should be nova. Nova is a transient luminous object. The luminosity is as high as 10 to the 5 times solar luminosity. So that is a kind of luminous object. But supernova is supernova, so it's much brighter than novae. The luminosity is of the order of 10 to the 43 erg per second. So supernovae are very luminous objects. And there are some classifications of supernova. So observationally, there are two types. First one is type 1 supernova. That is defined as no absorption lines of hydrogen in the photon spectrum. And among type 1, there are subclasses depending on the spectral types. If there is silicon 2 absorption line or singly ionized silicon absorption line, then it is called type 1A. If there is neutral helium absorption line, then that is 1b. If the spectrum doesn't include both of silicon and helium absorption lines, then it is classified as type 1c. On the other hand, if spectrum have absorption lines of hydrogen, then it is called type 2. Type 2 is also divided into subclasses, depending on light curves or luminosity evolution. If the light curve, that is, the trend of the luminosity as a function of time, if that curve is plateau, then that is called type 2p. If you can find the linear decrease of magnitude of luminosity, then it is called type 2l. So there are several types observationally. And theoretically, it is considered that this type 1a is corresponding to thermonuclear explosion. And other supernovae are core collapse supernovae. This is one popular model for thermonuclear explosion. One star has carbon-oxygen white dwarf, and mass accretion occurs for this star, and carbon-oxygen core mass increases gradually. And once the core mass becomes larger than the Chandrasekhar mass limit, then it gravitationally collapses. And inside the star, carbon burning explosively occurs. Then thermonuclear explosion occurs. On the other hand, core collapse supernova is considered as the final state of the stellar evolution of massive stars. After several steps of nucleosynthesis, nuclear processing, iron core forms in the center. And when the iron core mass becomes larger than Chandrasekhar mass limit, it gravitationally collapses. That is corresponding to core collapse supernova. In core collapse supernovae, large amounts of neutrinos are emitted. So yes, this neutron emission occurs at the end of the evolution of massive star. Initial stellar mass is larger than about 10 solar mass. After hydrogen, helium, carbon, and other nuclear burnings, there is an iron core. Because iron peak elements are the most strongly bound nuclide. It doesn't generate energy by fusion. And when the mass of the core becomes the Chandrasekhar mass limit, it starts to collapse. Temperature and density increases in the center, and photodisintegration of iron occurs. When the central region approaches to the nuclear matter density, collapse stops and burns occurs. And a shock propagates outward. At the inner, dense and hot region, neutrinos are copiously produced and it escapes from the central region. If the momentum, a part of neutrino momentum is absorbed or transferred to the gas, then gas start to explode, and it induces supernova. And in this core collapse supernovae, large amounts of neutrinos produced by central region affects the nuclear reaction or nuclear yield. And that is the topic dealt in this lecture. As I told, core clock supernovae are important producers of neutrinos. Iron core is about 1.4 solar mass, and it collapses to a neutron star. At that time, gravitational potential energy of this amount is released, and this energy escapes from the neutron star as neutrinos due to its weak interaction. It freely escapes from the central region to the outer layer. Yes. And typical number of neutrinos emitted by one supernova is 10 to the 58, because released energy is this size, and typical energy of one neutrino is 10 megaelectron volt. So some part of these emitted neutrinos scatter with matters in the outer layer. Then it helps explosion of the supernova. So here we show the solar system abundance in logarithmic scale as a function of nuclear mass number. Wide range of abundances of nuclei exist in the solar system. And here is a dip of abundance: lithium, beryllium, and boron. Lithium-7 and boron-11 is produced by supernova neutrino process. And also rare p nuclei such as tantalum-138 and tantalum-180 are produced. And short-lived nuclei such as niobium-92 and technetium-98 are also produced by supernova neutrino process. So yes, they are the target. Second, neutrino oscillations. One of important neutrino properties is its flavor change. Let's see what is neutrino oscillations. For neutrinos, mass eigenstates are different from eigenstates of weak interaction. And wave functions propagates as a function of time in mass eigenstates. Associated with the propagation in mass eigenstates, flavor can change during propagation. This equation shows the relation between weak eigenstates and mass eigenstates of quarks. This is related by this matrix called Cabibol-Kobayashi-Maskawa matrix. So strange quark as well as down quark couples to up quark. So the coupling is not so simple. Similarly, this shows the relation between weak eigenstates and mass eigenstates of neutrinos. This matrix is called Ponte-Koipo-Maki-Nakagawa-Sakata matrix. So the relation is similar to that of quarks. First, let's see neutrino oscillation in vacuum. For simplicity, let's consider two-flavor neutrino case. Let's assume that neutrino with flavor alpha is produced at time t equals to 0. So yes, this is a flavor alpha. And through the unitary matrix, this is related to the mass eigenstates. For the case of two-flavor example, for example, electron type neutrino at time t equals to 0 is yes, described by this form. This is explicit example for this equation. And this neutrino with flavor alpha propagates, and at time t it becomes this equation. Because propagation occurs in mass eigenstates, this phase factor is added here. This is one example, explicit form. Then, amplitude for transition from this initial state to the state nu beta is given by the inner product of these states. And that becomes this quantity. And here we use this ultra-relativistic approximation. So this is similar to the non-relativistic approximation, but we assume that momentum is much larger than the mass of neutrinos. So yes, this approximation is used. And with this equation 1 is transformed to this form. So neutrino with flavor alpha at time t is expressed by this one. Some overall phase factor and unitary matrix and diagonal terms and u dagger and nu beta. And here we just printed the same equation from the previous slide. And we define a mass matrix that satisfies this equation. Then this is rewritten in this form. By looking at this equation, you can see that nu alpha at time t is a solution of these types of Schrödinger equation. We note that here the common phase factor was dropped because it doesn't affect the neutrino flavor change probability or the amplitude of the transition from flavor alpha to beta. Yes, this is the same equation. And we are now dealing with two flavor cases. And let's take the unitarity matrix as given by this equation. Then m dagger m becomes this form. And we use the previous equation 3 and use this equation. Then nu alpha at time t can be expressed by this equation. Again, the common phase factor was dropped. So this is the same equation. Then let's consider the transition from electron type neutrino to electron type neutrino. It is given by the inner product of nu et and initial nu e. So it picks up this part. And transition amplitude is this one. And the transition probability from electron type neutrino to electron type neutrino, or it is called survival probability, is given by the square of the amplitude of this transition amplitude. And you can get this expression. As this equation shows, neutrino oscillation occurs in a vacuum. Neutrino oscillation means the oscillation of this flavor change probability or the survival probability as a function of time. On the other hand, transition from nu e to nu mu is also calculated using this expression that is given by this equation. Flavor change probability from nu e to nu mu also oscillates. Yes, these are Neutrino oscillations in vacuum. And we introduce oscillation length L0 by this equation. Then transition probabilities measured at the distance L is given by these equations. And these probabilities oscillates as a function of distance. But if the length scale is much larger than the oscillation length, then the oscillation signal disappears. In this case, its time dependence oscillates rapidly, and in fact, it reduces to the average of these quantities. So in this time averaged oscillation, loses the information of oscillation. If this is the measured quantity, we cannot get the information of the oscillation length. We can get only the mixing angle information. Next, let's mention the end of Neutrino oscillation. Neutrino oscillation stops when waves of mass eigenstates 1 and 2 separate. This figure shows the evolution or propagation of wave packets of mass eigenstates 1 and 2. Assume that electron type neutrino is produced here, and because of the neutrino property, the flavor eigenstates are described by the linear combination of mass eigenstates 1 and 2. And propagation starts partially as nu1 and partially as nu2. These different mass eigenstates has different mass, so they have different velocities. For example, velocity is given by this approximate equation. Here, ultra-relativistic limit is taken. Because of this relation, the velocity difference between eigenstates 2 and 1 is given by this form, proportional to the mass squared difference. So, after some long propagation, the center of the wave packets for different eigenstates are separated. When the wave packets separate, then oscillation stops. That is because neutrino oscillation in flavor change probabilities is caused by the interference between waves of eigenstates 1 and 2. So if wave packets separate, interference doesn't occur. And these mass eigenstates 1 and 2 are independent with each other. So there is no oscillation in flavor change probability. Neutrino parameters such as mass square difference and mixing angles has been measured by many experiments. One of them is Diabei experiment in China. Diabei is here, east side of Japan Peninsula, on the west coast of the Diabase. And mixing angle between mass eigenstates 1 and 3 have been measured using μe bar produced in reactors. This figure shows survival probability as a function of distance for electron type antineutrino. And mixing angle θ13 has been measured. And this figure shows the confidence limit on the parameter plane of sine squared to θ13 and delta ME squared. That is the mass square difference relevant to the electron type components. And by assuming these best fit parameter, the survival probability is well fitted. Yes, so mass square difference and mixing angle has been experimentally determined, as well as another parameter, CP violation phase. So let's see what happens for neutrino oscillation in matter. In stars and neutron stars, there are many baryons and electrons, but temperature is low, of the order of 10 megaelectron volt, less than 10 megaelectron volt. At this low temperature, there are abundant electrons and positrons, but no muon and tau. Because of that, charged current reactions is possible only for electron type neutrino and anti-electron type neutrino. So electron type neutrino can interact via two types of reactions shown here, Z exchange and W exchange. On the other hand, mu type and tau type neutrino can only interact by neutral current. And yes, this interaction corresponds to this Hamiltonian. And this becomes the potential shown here in the neutrino propagation equation. So this is additional term due to the electron background in the star. Because of this component, maximal conversion of electron type neutrino to mu type neutrino occurs even for small mixing angle. That is found by Mikhail, Smirnov, Wolfenstein. So that is called MSW mechanism. But yes, this is the term caused by the electron background inside the star. So let's define effective masses and mixing angle in matter. That is, yes, defined by this equation. Tilde correspond to the quantities in matter. If this Hamiltonian is diagonalized using this mixing angle, then the mixing angle is related by these equations. Here, delta m squared is the mixing mass square difference, and A is proportional to the electron number density. And for these typical values of physical quantities, neutrino energy, matter density, and electron mole fraction, A correspond to 7.6 times 10 to the minus 5 electron volt squared. And this is defining the effective mixing angle in matter. And effective masses in matter is defined by this equation. Then, this figure shows the effective mass squared as a function of electron number density. And also this is effective mixing angle as a function of electron number density. And this upper and lower branch of the solution correspond to m1 tilde squared and m2 tilde squared. These curves approaches with each other at this point. It corresponds to the electron number density given by this equation. And if electron number density is much smaller than this critical number density, then theta squared and m tilde squared, theta tilde and m squared tilde approaches to the vacuum value. And if n is much larger than the critical value, then mixing angle approaches to pi over 2, yes, as apparent from this definition. And also L tilde is affected. Oscillation length in matter is given by this equation. Here L0 is the length in vacuum. That has this typical length for this energy and mass squared difference. Because at high electron number density, A is very large. So this L tilde is much shorter than L0. And maximal mixing corresponding to theta tilde is pi over 4 occurs at the electron number density corresponding to critical value, this value. At that time, at that position, this mixing matrix becomes this one. So electron neutrino and mu neutrino is equally contributed to by the mass eigenstates of 1 and 2. Okay, so let's see how neutrino propagates in stars. Let's assume that nu E is produced in a region of high electron number density, and it propagates into a region of low electron number density. If the density gradient is small inside the star, then neutrino conversion occurs adiabatically. In that case, the neutrino state evolves following this branch. Then, full conversion from electron type neutrino to mu type neutrino can occur. And let's see. This equation shows the relation of the flavor eigenstates and mass eigenstates in matter for neutrinos. In the central region, theta tilde is close to pi over 2. So this is almost 0. Cosine theta tilde is almost 0. Sine theta tilde is almost 1. So nu E is corresponding to nu 2 tilde. So this upper branch is contributed by nu E. But at low electron number density, this is the relation in vacuum. And if theta is very small, smaller than 1, then cosine theta is almost 1 and sine theta is very small. In that case, nu E is dominantly contributed by nu 1, and nu mu is dominantly contributed by nu 2. So nu 2 here is almost nu mu. Then, after this propagation, nu E changes to nu mu. So, this is, yes, the flavor change through the MSW resonance between the center and the outer region of the star. Okay. So there is adiabatic condition that is given by this expression. Energy gap times transition time is much larger than the reduced Planck constant. Energy gap is given by this equation near the level crossing point. Delta T is given by this expression. That is the travel time over the distance of transition. And the MSW resonance occurs at the parameter A given by this quantity. And its width is given by this quantity. So this adiabatic condition becomes this inequality. So in order to have large conversion from electron type neutrino to muon type neutrino, some condition should be satisfied in this parameter plane of log delta m squared and log z. Z is defined as this ratio. As one condition, at the production point of neutrino, electron number density should be larger than some critical number density. This defines this condition. And we need that survival probability of electron type neutrino is less than 1 over 2 to have significant conversion of flavor. So this defines this line. In addition, we need adiabatic condition that correspond to this line. And significant conversion from electron type neutrino to mu type neutrino is realized in this triangle. This is called MSW triangle. Finally, let's see how is numerical solution of neutrino oscillation. First case is two-flavor oscillation in a constant electron number density. The Schrödinger equation for this case is given by this expression. And squared mass, effective mass and electron potential has been already defined here. And this figure shows the evolution of coefficients of wave functions in vacuum as a function of radius or propagation distance. For these left panels, we assume that initially neutrinos are produced as electron type neutrino. Then phase of the wave function changes. Also, a new mu component of wave function evolves. These right panels shows the case of initial mu neutrino. So it has typical oscillation length scale, and both of real part and imaginary part of wave functions evolves. And the oscillation period is the oscillation length in vacuum, L0. How about transition probabilities in vacuum? This figure shows calculated transition probability for the transition from alpha to beta. And it agrees with analytical solution in the vacuum oscillation case. In this transition probability, there is only one characteristic radial scale. This period. If we take these neutrino parameters and neutrino energy, then oscillation length is 300 kilometers. Then let's assume some finite electron number density. This figure shows the result for the electron number density corresponding to this matter density and electron mole fraction. So this result is somewhat different from previous case. Again, these are for initial electron type neutrino case. These right panels are for initial mu neutrino case. The coefficient of wave function is described by the superposition of two sinusoids of different lengths. In this case, the scales are this one and this one. And again, this is showing the transition probability for this density and electron mole fraction case. In the flavor transition probability, we have typical period that correspond to the oscillation length in matter. In this case, L tilde is 100 km. So, oscillation length depends on the electron number density. Finally, let's see the case of three-flavor oscillation for general density profile of electron. That case is shown by these equations. Here, del time 2-1, del time 3-1 squared. These are mass squared differences. And U is a matrix given by this expression. And from various experiments, neutrino parameters has been measured as shown here. One uncertainty is the neutrino mass hierarchy. So, there are two possible cases of delta m 3-2 squared. It may be plus or minus. It means that there are two possibilities, as shown here. This figure shows the mass eigenstate eigenvalue for state 1, 2, and 3. One possibility is normal mass hierarchy. Third mass eigenstate is above mass eigenstate 2. Another case is inverted mass hierarchy. The state 3 is below state 2. In normal mass hierarchy, there are two light mass eigenstates and one heavy eigenstate. In inverted mass hierarchy, on the other hand, there are two heavy states and one light state. This hierarchy is not yet determined so well. So this is the uncertainty remaining for the neutrino parameter. And this figure shows the three-flavor oscillation in a constant electron number density. transition probability as a function of radius is shown for the transition from electron type to electron type, and electron to tau type, and electron to mu type for this energy and density. And in the case of real star, density of electron depends on position inside the star. In that case, transition probability becomes this one. This is transition probability as a function of Lagrangian mass coordinate inside the star. So this is indicative of the stellar position. This is inner region. This is outer region. For example, MR equals to 2 solar mass correspond to the location at radius r. Inside that radius, 2 solar mass is included under the assumption of spherical symmetry. So this is inner region, this is outer region. And here, the flavor change probability significantly changes. This corresponds to MSW resonance. And here, nearly complete transition of electron type neutrino to mu and tau neutrino occurs. And if the Schrödinger type equation introduced here is simply solved, this is a solution. P mu e and P tau e oscillates very frequently. But the sum of P mu e and P tau e is 1, almost 1. Then, this figure shows the flavor change probability of neutrino and antineutrino as a function of stellar location. PEE is the flavor change probability from electron type neutrino to electron type neutrino. This is X type neutrino to E type neutrino. X contains mu and tau type neutrino. And this dashed line corresponds to the probability for antineutrinos. So, inside the supernova, neutrinos changes flavors due to the electron distribution inside the star. Okay, let's summarize today's lecture. Firstly, neutrinos interact only weakly, and there are 2 types of reactions: neutral and charged current reactions that operate in stars and supernovae. Neutrinos are very light and produced in various astrophysical sites. Inside the core collapse supernova, 10 to the 58 neutrinos are produced. And some stable nuclei observed in solar system are produced by supernova neutrino process. Then, neutrino flavors change during the neutrino propagation. Mass eigenstates and flavor eigenstates are different for neutrinos. Because of that, neutrino flavors change. And neutrino oscillation occurs due to interference of different mass eigenstates. And that oscillation ends when the wave packets of different mass eigenstates separate. In dense matter, the mixing angle and oscillation lengths of neutrinos are different from those in vacuum. Oscillation length is much shorter in denser region. And in supernovae, flavor changes of neutrinos occur through MSW resonances, originating from the electron potential inside the supernova. Let's finish the first part of the lecture